So this is one of the really exciting projects that's happening in Java. And why do we need these? You've already heard my elevator pitch as to why these might be useful. First of all, I'm sure a lot of you have worked with asynchronous code, and when it works, and it's great. It's a really well thought out, and there are lots of little ideas. But if something goes wrong, it can be quite tricky to debug. So the reason why we would even consider that asynchronous code is because we are quite limited in how many native threads we can start. As I said in the preamble, with on my little machine, my little laptop, I can start 16,000 threads, and then I get out of memory error. So, and I don't even want to get close to that. And of course, we don't want to write systems where we fall over if you get a sudden surge of users coming to our system. So this is where Project Loom comes in. We can make millions of virtual threads in a single virtual machine. And it's supported with networking. So if you're waiting on the socket, your thread will be swapped out and by the virtual machine. And another thread will be swapped in. And if you're doing lots of networking, you're going to be waiting on the sockets most of the time anyway. And so it's a really good model. Similarly, if you are waiting on any of the Java till concurrent constructs, that is also compatible with Project Loom. And you'll get blocked out, you'll get swapped out, and other threads will be swapped in. So I've got a little scenario here. Let's say that you want to have a website which looks for really great deals. So you, first of all, scan the request for search terms, what to look for. Then you launch off a bunch of searches on partner websites. You also create advertising links because, of course, you have to make money somehow. So advertising will probably be the way. And then you need to collate the results from the partner websites and bring it all together and present the website. Now we can reorder some of these steps a bit. For example, we can create advertising links first and then do the partners after that. But in the end, we need to have the final answer. And the simplest is to do it sequentially. So a request comes in, and we step by step go through it. We start the search. We go through all the partner sites one by one, do the request, search them, and then we do the advertising links. And then lastly, we collate the results, we get all the results, and we build this website, and we present it. And this is the simplest, but of course, we've got this whole problem with latency. It might cost us a few milliseconds to send them a request to the partner site and then wait for them to answer. In the meantime, we could do something else. In a way, it would be the easiest if we could just make one thread per request, but the problem is native threads are limited in terms of how many we can make. And so if we just arbitrarily construct new, more and more threads, we're going to get an out-of-memory error. So that's what we want to try and avoid. So I added some time budget to each of these steps. Of course, 42.5 seconds is unrealistic. If you take that long, they're going to go somewhere else. But just imagine that everything together, if you do it sequentially, one after another, will take 42.5 seconds, giving it some number. Now, we could use callables and futures and an executor service. And so what we could do is we could start the search on all the partner websites in the background using a callable. And we might get better performance because hopefully by the time we finish the advertising links, some of the background searches have already been completed. And so by the time we need them, maybe they're there. And so this is the code. I've got a callable. So the code before, where I did the search on the partner sites, I've just simply wrapped inside a callable Lambda. And I've did it explicitly just to show what's going on. So in the bottom of the screen, you see the callable there. Search the task, and I give that to my executor service. And now things get a bit tricky, because the question is, what type of executor service should I use? Should I use a cached thread pool or a fixed thread pool? If I use a cached thread pool, I again run the risk that if lots of requests come in, that I run out of threads and I get an out-of-memory error. And if I use a fixed thread pool, I run another risk that if the system's busy, we start getting a backup queue of tasks which still need to be done, And of course, in that case, you might wait more time in the queue than you would have waited if you just done it yourself. It might exceed the 42.5 seconds by quite a big margin. But there's another problem, and that is that we are only fetching all of them together in the background, and we're really only doing the advertising links in parallel with the fetching. So our performance doesn't get much better than what we had before. Seems like a lot of work for not much gain. And of course, you could go for the, the Java 8 onwards approach of a completable future. And this is a great little model, completable future. Normally what you do is you draw down an activity diagram, and each of the different steps would be its own completable future, which is then executed asynchronously. And then you combine all of these with all of. I'll show you the code just for fun, but it is a little bit more complex. And it is faster because we can do more things in parallel, but it is a lot more complicated. And another thing you have to consider is, in this case, I'm going to separate the CPU-based tasks and the IO-based tasks. And the reason is that when you configure the sizes for your pools, you always want to make sure that you do it for the correct type of task you're going to do. If it's CPU bound, you want to have it pretty close to the number of hardware threads. And if it's IO bound, you're going to want it quite a bit larger than that, but not exceeding that maximum that will make your virtual machine crash with an out-of-memory error. So this complicates it even further. We can't use just the common fork join pool because, well, those common fork join pool threads are used also by other parts of your system for parallel threads, for example, parallel streams, for example. And so we can't use that, unfortunately. And so here's the code. I'm basically, every task has become a completable future. And I've got, for example, at the bottom for the advertising links, I've got my own completable future, which does it asynchronously using the render pool. And then I've got another one which does the scan for search terms again with the render pool. And then further down, I've got the search on partner site with the download pool. So I've got different pools for each of the tasks. And it's like 3 slides instead of 1 slide, which is great if you're counting lines of code. And our performance is actually not that bad. We could get it to be faster, but I have limited the number of threads in the download and render pool to be a bit more realistic, because if you have an infinite number of threads, well, that'll be great, but not really what you're going to do here. I've got a little gift for you if you're interested. Go there, tinyurl.com/JDConf. You'll get a gift. It's an offer which expires at the end of this talk, so if you don't get it before then, you won't get it. So if you're watching the recording, sorry. Here's the link again. Now, we get to this idea of Project Loom and virtual threads. The virtual threads are very lightweight, typically less than 1 kilobyte, but it depends what you do with them. They are very fast to create. I tried a little demo earlier on today, and I made 23 million virtual threads within 16 gigabytes of memory. So I've got a 64 gigabyte machine, and 1/4 of that is allocated by default for my memory, and so I made 23 million virtual threads. And it's just a bit over half a K. It's about 600 bytes, but it depends what you do. In some cases, it'll be a bit more. I've seen it go sort of 1.5 kilobytes, but round about there. And the actual threads that execute these virtual threads are what we call carrier threads. And the carrier threads are by default at the moment normal Java threads from inside a fork join pool. Fork join pool is a really good option for this type of for these carrier threads because it's good at executing short jobs. However, you'd have to be careful because we managed to exceed the queue size of the tasks on the fork join pool. So we actually created too many virtual threads too quickly, and the task queues of the fork join pool are limited to 64,000 tasks. And so we actually blew that budget. You've got to be careful. Something else is that the carrier threads are by default daemon threads. So you need to make sure that all your work is completed before you actually exit from whatever method you're using there. The number of threads in the fork-join pool is by default the number of available processors in your system. So the number of hardware threads. And this can temporarily increase due to the managed block. I'll talk about that again in a second. And what's also really cool is that if you have a virtual thread and the virtual thread blocks on I/O or sleeps or waits on a Java concurrent construct like a blocking queue or reentrant lock, then that virtual thread basically gets swapped off the carrier thread using continuations, and once it's ready to do some more work, it gets swapped back on again. And this is all happening without us having to change our code. Super convenient and really great system. Let's get back to the single-threaded renderer. So this is what we started with, and we had all this code of one after another, and if the threads were unlimited and free, why don't we just create a new virtual thread for every single task? Now, of course, nothing is unlimited in the world except for human stupidity. I think that is unlimited and knows no bounds. But besides human stupidity, threads do have a limit. You can't make unlimited number of threads. I wrote this one experiment and I was running it to see how many threads I could start. And I would start a thread and park it, and then start another thread and park it, and start another thread and park it. And it ran and ran and ran. And I let it run overnight. And the next day I looked at it and I said to my colleague, I said, hey, John, look at this. We've got 17 billion virtual threads started, and they're all parked. And then I sort of did the math and thought, wait a moment. I've only got 16 gigabytes allocated to the process. So is it like less than 1 byte per virtual thread? No, of course not. So that was a failed experiment, and my experiment was flawed. That's why it seemed like it. So nothing's unlimited, but the limit is really high. It's much, much higher than what we're used to. All right. Now, here I'm creating a new virtual thread for every task. So what I'm doing is, first of all, I'm starting a virtual thread to create the advertising links. That was the third step. Then I scan for the search terms. I do that with the current thread, and then for each search term, I start another virtual thread, and the virtual thread will search on the partner sites and then collate the results. So that's how I do it. And then I get back a collection of all the threads that were launched like that. Now, launching these threads is really cheap. So launch. And then afterwards, I join all the threads which I've started in order to make sure that I'm finished with all the rendering before exiting from the method. So I wrote this code and I thought, doesn't feel that great. It just, it didn't feel so good, and but the speed was great. From 8.5 seconds down to 4.5 seconds. So in fact, from 42.5 seconds all the way down to 4.5 seconds. So really great performance, but it didn't feel good doing all these joins. I didn't like the joins particularly. Also, if you look at the top, you'll see there's an interrupted exception being thrown from the method. Again, it's like, why do we have all this stuff? So there are two ways you can create these virtual threads. Either you can make individual threads with thread.start virtual thread, and they've added a thread builder, which allows you to make a normal thread builder. You can specify whether or not you want thread locals, etc., and then start the one thread. There's also a virtual thread executor, which will just construct more and more threads uncontrollably until you're done, until you finish with your program. And what's really cool, really super cool, is that executor service is also now auto closable, and the close method calls shutdown and then await termination. So that's a really great feature, and I believe this is actually not directly only because of Project Loom. I think this is coming into Java version fairly soon, and this allows you to do something called structured concurrency, where I'm saying I put in there, I create a new virtual thread pool. And remember, these things are very cheap to create, so we can just create them without worrying about the cost. And then I've got I submit my one job as where I create the advertising links. And then another thread, another job where I do the other work. But internally, I've got a nested executor service, which I put in there. So, and because they get closed at the end, I'm also sure that everything is completed by the time I exit from the method. So this is really a nice way of working. Time is the same as before. Now, there are some things to know. Manage blocker is one thing. Manage block allows the fork join pool, which is what the carrier threads are using, to create more threads if you block. And in Java 7, only the phases supported this, but Java 14 abstract queued synchronizers supports that, which means reentrant block. Therefore, all the blocking queues also support this. So this means that if you do have to block, your fork join pool will create additional threads to keep your parallelism high. So this is also really convenient. Now, you might need to implement this in your own code base. Have a look in the JDK how to do manage blocker. The Java IO implementation was rewritten. So in Java JEP 3.5.3, they re-implemented the legacy socket API. So they took the plain socket impl and they replaced it with the NIO socket impl. And then the JEP 3.7.3 re-implemented the legacy datagram socket API. And when I saw these numbers, I thought, this is like, I can imagine them like when you try and get a really cool license plate number, you're like waiting for the numbers to tick over so you can get the really good number. So I wonder if they were waiting for the JEP to tick over until the number 3.7.3 and then, let's get that on as well. So 3.5.3 and 3.7.3, easy to remember. I don't know. Anyway, something to remember is that at the moment, synchronized wait is not yet compatible with Project Loom. And what will happen is that the virtual thread will store the underlying carrier thread and won't allow it to be swapped out. And this happens specifically if you call a native method whilst holding a lock. And monitor.wait is a native method, therefore synchronized monitor is at the moment not going to work. So if you here are making as many virtual threads as I've got hardware threads, and that's how many carrier threads I've got by default. And so when I try and add one more virtual thread, it won't actually be executed. So everything will just stop. So don't do that. And but the synchronized works in general. It's just if you wait, that's not going to work at the moment. But they are working on fixing that sometime in the future. So we might have to change our code to use reentrant lock and stamp lock. And in both cases, reentrant lock and stamp lock, the idioms are more complicated, but at least you can be compatible with virtual threads. Another thing which might have an impact on your system is that biased locking is turned off by default. And I understand that biased locking does complicate things quite a lot. And so what they've said is let's not keep on supporting that going forward. Biased locking should not have a huge impact on your performance. But I have got some benchmarks that show concurrent hash map being 3 times slower in an environment where you don't need locking. So if you don't need synchronization, you don't need thread safety, but you're still using concurrent hash map, it might be 3 times slower with biased locking turned off than with it turned on. But I'll be very surprised if in your real application you would measure a difference. But this has been off since Java 15. So what you can do is if your application runs slower in Java 15, turn it on again and see whether that makes a difference. I would be very surprised if it does, but please report if it does make a difference. It shouldn't. And if it does, you might have to find the place where this is a problem. It's not so easy to find these. Good luck. Also, thread local is problematic. There's a better solution with Project Loom called scoped variables, which you should rather use. And they weren't sure about whether they should support thread local or not. They do, but you can turn it off. Thread locals also often don't make sense because virtual threads don't get reused. They're so cheap to create, they just get thrown away afterwards. we've got a server running at the moment where the server component has 2 million sockets open and 2 million virtual threads on a little machine. It's not a huge machine. It's got 6 cores, 12 hardware threads, and 2 million virtual threads running right now. And all I'm doing is pinging backwards and forwards with the clients. The clients are running on the same machine, one huge virtual machine with, again, 2 million virtual threads, pinging backwards and forwards. And when I first wrote the code, I did the client code with an input stream reader and a buffered reader to read the data and a print stream to write the data. And I couldn't understand why the client, because I did that on the client, used so much memory until I did some investigation into these streams. So this is something which really surprised me. The print stream uses 25 kilobytes per print stream, right? And if you only use 3 print streams, it really doesn't make a difference. But if you create 2 million print streams, all of a sudden you've got 50 gigabytes of memory just wasted, an empty space of buffers for print streams. Your buffered reader is 16 kilobytes because it's a 8K char array, which is 2 bytes per char. And then you've got the adapter, which is 8 kilobytes, input stream reader, 8 kilobytes. So altogether, it's like 50 kilobytes per buffered reader and print stream pair. So be very careful with that code. I'm very excited about this Project Loom. I think it's a great job. You can download it from the Project Loom website already. Play with it, try it out. Obviously, if you're using production, make sure that you check your check your server regularly. Before I got onto the talk, I checked my Java Specialists EU website, the link here, and I discovered to my horror that I forgot to renew my SSL certificate. And I discovered it like 15 minutes before getting on air. So, oh no, this is terrible. And it takes a bit of time to renew that. So if you go there now, you'll see insecure. Don't go there. Don't go there. Hopefully, it'll be working properly again tomorrow. Don't forget the gift, and do try out Project Loom, because it's a project which has a lot of potential, I think. And it should make debugging of our systems a lot easier when we can follow one stream from top to bottom rather than all sorts of asynchronous method calls that are sometimes very hard to follow. So that's it from me. Do we have any questions?
Hey, Heinz. First of all, congratulations. That was a great talk. We got some great feedback from Twitter. Not Twitter, I'm sorry, YouTube.
Oh, cool.
There's one question here. If a framework heavily relies on thread local, such as Spring Security, can't they move to Project Loom now?
Yeah, it could. You can use thread locals. They actually are on by default, but it is recommended to move away from that because each time that you've got a thread local, each time you set a thread local value, it creates a thread local map, and that's quite expensive in terms of memory usage. I'm not sure how much it uses, but it's substantial. So recommended is to try and move away from that at some point.
Okay. One question that I have.
Okay.
A few months ago, I was benchmarking gRPC servers in Java, and I came to the point I had to deal with thread pools. Once we moved to Loom, yeah, I think you saw that.
Yeah, we had a discussion about that. I do remember.
Exactly, yeah. You went to the GitHub issue and you said, "No, Bruno, you're all wrong. This is how it should be done."
No. Your benchmark's wrong. Not you. You're not wrong. You're right. Just the benchmark is flawed.
So the question I have for you is, with Project Loom, do we still need thread pools?
No, all you'll do is you'll just say start virtual executor service or virtual thread executor, and you're done.
So no need for thread pools.
Well, that is an executor service. I saw there was one question about callable. You can submit callables to the thread pool executor. No problem. You can work with callables, futures, all of that. You can even work with computable futures. All of that is completely operational together with Project Loom. So they work together. You still have the higher level threading constructs. But for your, was it GPRC or whatever it was, for that, you would simply pass in the virtual thread pool, and or rather virtual thread executor, because it is not technically a pool, because the threads are always thrown away afterwards. They don't go back into the pool. You make them, throw them away, make them, throw away. They're so cheap to make, you might as well throw them away afterwards.
So it's an executor service, but there's no need for a thread pool algorithm in the behind the scenes to be managing those threads, because you just create one, you execute, and you're done. That's
right.
it.
Right.
Okay. Exactly. I should try Project Loom on my benchmark.
Yeah, you should. You'll get amazing results with that benchmark of yours.
I'll give it a try.